if this is the form for f of x, and if the function has three distinct solutions which are real, then we would like to narrow down the intervals in which these three roots will be. And so this is not it's not easy to see from the first time, but it is good practice to recall the statement of Rolle's theorem. So this is the statement. And what Rolle's theorem is telling us basically is that if your function is continuous, so you can draw it like I did here without lifting the pen, and you have 2 points at which they are equal. So A and B are points at which the function is equal, so it has the same height. F of A is equal to f of B. Then there is a point C at which the derivative is equal to 0. What this means basically is if you're drawing your function like this and you're going back to the same point, same height I could say, then there is a point at which the rate of change, or the slope is more important, is equal to 0. And the zero slope is like this. So this is zero slope, because if you think of a straight line that's like this in the plane, then it's just a constant. It's probably y is equal to 1 or y is equal to any value that you like. So this is why if the derivative is equal to 0, then you have a line that's tangential to the function at that point. And so this could also happen in the other directions. You'd have something like this, or even something that's more complicated. But the idea is that there will always be a point at which the derivative is equal to 0. And so what I mean by this is there's always a point at which the function is, let's say, decreasing and then it increases, or it's increasing and then it decreases. That's the conceptual understanding that I would like you to have. There's of course the case where it's just a constant function. In this case, the function is not really increasing or decreasing, but in that case it's nice because we have infinitely many points for which the derivative is 0, which are namely all the points in the interval. So that is also a good visual image to have. But then how do we use this? Well, here's the idea. If we find the derivative, we set it to be equal to 0, and we know that this function is continuous. It's continuous because it's an addition of continuous functions, all of these. And so we know that there will be, if this is true, if the derivative is equal to 0, then this is implied by this fact. So it's like we're going in the other way. This is not always true, but if these conditions are true, and we know that there are roots, so we know. So what is a root? It is a point at which f of A is equal to f of B is equal to 0. Then we know that there are C's which are in the middle between the zeros, which are the roots of the function. So let me start by taking the derivative of f. So 2x cubed, that's going to be 6x squared. 9x cubed, if I take the derivative, that's going to be 18x, I just multiply by 2. And the derivative of 24x is 24. And the derivative of a is 0. So that's good. And how about I try to find the roots of this derivative function? So there's something that I'll immediately do because it's bothering me. I can divide by 6. So 3, and then negative 4. And then this is not too difficult. You could use the quadratic formula, but yeah, and this will give you that you have x minus 2 x minus 4 and then x plus 1. Yeah. So in this case, the roots of f prime are 4 and minus 1. Correct? This is the set of all roots for f prime. So that is already hinting to us towards something. So if you would like to imagine this, so our setup is really not at these points, it's at the zeros of f. Let me repeat this, it's at the zeros of f. So we know if a function has a root, then it intersects the x-axis. So this is what I've set up here. And let's say for one interval, let's say from minus infinity until, let's say, minus 1. Okay, this is not accurate. And I would draw yeah, maybe I'll draw something like this. So this for example would be equal to minus 1. C would be equal to minus 1. That's what I want to say. Because C is a root of the derivative function. And so by Rolle's theorem, we know that there will be one root which is less than minus 1. Because if we want to apply Rolle's theorem, and we know we can apply it, and we know that it will give us this result, and then this is the point in the middle, you could say, that at which the function changes its derivative. So its derivative is first it's positive, and then it becomes negative. So it becomes downwards. But to go from positive to negative, you need to go through 0 rate of change, which is just this. So we know that it will be from minus infinity until minus 1. Let's go progress. And then we can do the same thing for 4. Let's say here I'm at 4. Let's say I have something that looks... By the way, this is all visual. It doesn't really signify anything that is real. We're just trying to set up the venue. The venue is here, actually. You need to at least conceptually understand why this is meaningful in this sense. So at 4, we have the derivative equal to 0 as well. That's what we've just shown. The derivative, so not the function itself. And so because the derivative is 0, then this point minus 4 is in an interval a and b, where a is equal to b. Specifically, you could say a is equal to b is equal to 0, because these are the roots. So there's a root. So there's always a root. There are always two roots which contain 4. So if you take the interval between two roots, it should always contain 4. And if you take the interval between two other roots, it should always contain minus 1. So it must always be that. So you can't have something that looks like this. That's what I'm really trying to say. You can't have this. because then your Rolle's theorem fails, and you have to move your derivative point, your c, to the middle, not precisely the middle, but something in between, because that's what it's saying. The c has to be in a and b. And so if this is true, then a and there should be one root that's before -1. There should always be one root that's after -1, and at the same time it should also be before 4. So, and we do this one more time, of course. It should be between 4 and, well, just go as far as you can, but don't go to infinity. Just take any finite number that's before infinity, and that should give you your answer. Finally, let me plot this function. So here I chose to plot the function where a is equal to 0. So I didn't write a, I just wrote 2x cubed minus 9x squared minus 24x. And if we take a good look here, we see that the first root is less than -1. The second root is less than 1. It's actually 0, I think. Yes, it is. And the third root is greater than 4. So it's 6. Now what happens if I add 1 here? So I add let's make it 4. Let's add 4, because why not? Then I add 4, so the function should be shifted upwards. Okay, then the roots are now -2, and then 0 point something, and then 6 point something. So that is not horrible either. But these are just examples. If you take any a, it will always be true that the first root will be always less than -1. The second root will always be between -1 and 4, and the third root will always be bigger than 4. That is really what we have just shown ourselves. So this is indeed a very, very powerful statement.